All right, this morning I'd like to go over some examples of Newton's second law, but instead of doing static problems like we've done before, we're going to go over some dynamic problems. Remember, when we approach dynamic problems, dynamic problems specify when our acceleration doesn't equal 0. Okay, so when we talked about static, we could just do some of the forces in the x and y, setting it equal to 0, and then solve for unknowns, because we know that a resultant vector was going to be 0. In these cases, we're going to have situations where an object is changing velocity. All right, so the object will be in movement in a dynamic problem. Here's an example. Let's do a problem like this. I saw a couple problems like this from another class the other day, and I think it would be good practice for us. Let's say you have a car that accelerates from an initial velocity of 0 meters per second to a final velocity of, 27.8 meters per second. All right, and that takes 5.8 seconds of time. Now, the mass of the car is around 1,400 kilograms. And we want to know what is the average net force, that's acting on the car. So we just want to know what F is. Now, in this case, if we look, our Newton's second law equation, F equals ma, we've got a lot of information that could go into this equation. For starters, we have our 1,400 kilograms that would go in for m. But we don't have our acceleration. Well, if we remember, our acceleration is Vf minus Vi divided by t, right? And so in this situation, we can look at this, we can say, well, I have all the information to solve for A. And so this actually turns into a pretty easy problem. We can go 27.8 meters per second minus 0 meters per second divided by 5.8 seconds. Now grab our calculator. 27.8 divided by 5.8, and you're going to get a value of 4.79 meters per second squared. Now at that point, that's what we plug in for our A, 4.79 meters per second squared. You're going to take that 4.79, times it by the 1,400, and you get a value of 6,700 newtons, roughly. It's actually 6,706. Now remember, a newton is a kilogram meters per second squared. But that's our final answer. Pretty simple. It's kind of just a plug and chug problem with only one part that we had to solve for before. Let's do another problem. A lot of these, now you'll notice we can pretty much make up any amount of problems that we want to, where I give you enough information for 2 of the items, and then we just solve for the third in F equals ma equation. Those can all, fall under that dynamic problem scenario. So let's say that I have an airplane, that can accelerate from 0 to 56 meters per second, in a distance of 80 meters. So we'll just say that's our delta x. It's 80 meters. And we want to know what the average net force is acting on that airplane. And so we're looking for F, and we have a mass of the airplane at 13,300 kilograms. Now here, once again, we look here, we go, well, F equals ma. That's pretty simple. So we'll just do F is equal to 13,300 kilograms. And then we look, well, I want to do my A, and so naturally, right off the bat, we'll probably come and we'll write out this equation, right? And then we start dropping in our values, and we go 56 meters per second minus 0, and then we realize I don't have time. I don't know how long it takes for that to happen. So you have two options here. Okay, option number 1. So first option. You can use this equation, which you have enough information for. Okay. Now, you might look off the top of your head and be like, well, we actually don't have enough information because we have two unknowns here. We have t and a that we don't know. However, we do have this equation for a that we can plug in right here so that we only have one unknown left. So that would transfer, that would make this transform into an equation that looks like this. Okay, and now in that case you only have t left over. And that's a pretty easy solve for t, especially when your initial velocities are 0 and your x initial would be 0. Okay. Second option is just solving for a directly without having to solve for time. Because notice the whole point of doing my first option would be to solve for t and then plug it back into my original acceleration equation to find my acceleration. If I can find another equation though that doesn't require time, then we can solve for acceleration without time. And we do have one such equation. Okay, and that would be this equation. All right, we've used it before, primarily because we don't have time for some problems. And so, in this case, we look at this, and my v initial here is 0. Okay, and I'm going to solve for a. So a is equal to vf squared divided by 2 delta x. So that's my equation. Now, either way works. You can solve for t here and plug it into this a equation, or you can just solve directly for a using this equation. Both options are valid. In this case, I'll do this one. This one seems a little easier. I'm going to put in 56 meters per second, square that, divided by 2. Okay, and then I have my delta x, which is 80 meters. Okay. Now, if you're wondering, does this work out units-wise? It does. It does work out units-wise because here this becomes meters squared per second squared divided by meters. So those meters cancel, leaving me with an acceleration value of meters per second squared. So my units check. That's how I know that I've got a good equation on my hands. So I would probably do this in sections. I'd do 56 squared first, get a value of 3136. And then divide it by 2 times 80 in parentheses. And you're going to get a value, an acceleration of 19.6 meters per second squared. Okay, now that right there, we're going to take and plug back in for our acceleration up top, 19.6 meters per second squared. Times that by the 13,300, and we get a value of 260,680 newtons. Most likely we would take that, then we would put it into scientific notation, so you'd get 2.61 times 10 to the 1, 2, 3, 4, 5 newtons. Okay. So once again, that problem seems a little bit more intense, but just recognize that that's all we're dealing with here. Okay, we're dealing with our F equals ma equation, and then we're just solving for the constituents, those parts that we need on the inside. Okay. Now we can also have some more simple problems. We can have problems that are simple as, let's say I give you a force, okay, a car is undergoing a force of, say, 10,000 kilonewtons, That's my F. And it's experiencing an acceleration of, say, 10 meters per second squared. And I just want to know, what is my mass? In that case, we start off with the F equals ma. Okay, and then we solve for our mass. So that becomes like this. But notice here, I have 10 kilonewtons. So when I plug this in, I can't just go like that. I have to drop that kilo on the front there. Okay, and I'm going to expand out its units so you can watch the units cancel. Make sure I get the right units out of it. And then acceleration is at 10 meters per second squared. Meters per second squared is canceled. We leave with just kilograms. And then you do your 10,000 divided by your 10, and you get 1,000 kilogram car. Okay, and now you have the right units there, so that works out. All right, so hopefully this helps. You can have, varying degrees of difficulty on these. One other scenario that I know some of you are going to experience is when we talk about various forces acting on an object. So let's say I have an object that is, let's say I'm pushing on the object with, say, 50 newtons. Okay, but then I'm experiencing like friction, okay, at a 5 Newton force with the ground. And then we want to know what, let's say, what is the acceleration? Okay, and let's give it just a value of, say, 10 kilograms, whatever the object is. If that's the case, then really what you do is you'll have to draw a free body diagram first and realize, okay, well, if I'm going to push it that way with 50 newtons, friction is going to go the opposite direction of 5 newtons. So we do our sum of the forces in the x. I'm going to get 50 minus 5 with the value of 45 newtons as my net force. Okay, my overall force, my resultant vector force acting on the object, and then that's the value I would use in my F equals ma equation as I solve for A. And so we'd have 45 newtons on top, we'd have the 10 kilograms on bottom. Okay, and so in that case we'd get 4.5 meters per second squared as our acceleration. Okay, so don't let those kind of problems scare you either, just because they give you two forces. You just have to find the net force first, then plug it into your F equals ma equation. Okay, if you have any questions on these, let me know. Obviously, there's a lot of different options of how we can make these problems. So be careful, go slow, write out your givens at the beginning of the problem. It really helps you identify which equations are available for your use. Okay, if you have any questions, come in, ask, or shoot me an email. My email is jared.bringhurst@washk12.org.